What is the most used man-made material on Earth? You guessed right, it's concrete. Look around. It's everywhere. Sidewalks, driveways, foundations, floors you stand on, and even entire buildings are made out of concrete. So why don't we discuss it more? In each episode of Concrete Logic, we will explore one concrete-related topic with the help from industry professionals that are shaping the future of the trade. We'll talk with suppliers, contractors, architects, engineers, specialists, and even some proponents of competing materials about their views of concrete and their vision of its future. And welcome to another episode of the Concrete Logic podcast. And today I have Robert Higgins with me. Robert, could you introduce yourself?
Oh, yeah. I've been involved with concrete waterproofing since 1976. And then in 1985, inadvertently, I started also doing some construction defect litigation, which really was eye-opening. And I started a company with my brother back in 1979 where we created waterproofing products and we grew to have a global presence. But I found that as we grew, it became more of a marketing situation, and I kind of lost my zeal for it because I love the research. I love going out and troubleshooting and problem solving. So I broke off in 2009 and became an independent consultant. And I've been an independent consultant ever since. And I've really, really enjoyed this. It's given me it's nice too because I don't have to watch what I say.
Yeah, that is nice. Yeah. So you're, and the way we connected is, as a lot of my podcast guests are, you're very active on LinkedIn, and there was a post that a fella, Josh Bong, he's a concrete guy out in Oregon, and he posted a picture of his work. And I always appreciate Josh's work. He does fantastic work. And he had a post. He was putting a slab in, and I saw something curious. The vapor barrier, which I'm accustomed to seeing. I'm accustomed to seeing the vapor barrier set on top of the base for the slab, and then the concrete's put directly on top of the vapor barrier. And Josh had vapor barrier, and then it looked like he had a layer of sand, and then he was going to put concrete on top of that. And I was like, Josh, what is that? Why is the vapor barrier below that? And he's like, that's what they specify out here. And then you chimed in and you said, hey, this is something we need to talk about some more. And so you put it out there, and I guess I took the bait and said, come on, Robert, let's talk about it.
Well, yeah, I disagree with the sand bed because that encourages capillarity. But if you use a larger graded stone, it's a great capillary break. And what it does is allows the top portion of the concrete and the bottom portion of the concrete to become their own gradients. So, and why I don't like a vapor barrier directly below a concrete slab is it won't dry. Now, what will happen when it doesn't dry and the surface dries too quickly, you get curling and map cracking. And that's become almost epidemic, and it's gotten worse, steadily worse since right around 2002. And then about right at the end of 2018, going into 2019, it's become a national issue because cement now is more alkaline than it used to be. The concrete that you're placing now is not the same as it was prior to 2002. Where we are in the country.
Yeah, I don't mean to interrupt you, Robert, but what we want to do, I think first, let's explain what a vapor barrier is, and what its intended use is for, because we want to make sure everybody listening understands what we're talking about first. So could you explain what a vapor barrier is and maybe the origin of using a vapor barrier?
This will be a little controversial. The origin of a vapor barrier was based quite a bit on a study that was done by the Portland Cement Association back in 1965. That's called, a lot of people refer to it as the Brewer study. Now, the Brewer study was entitled Slab-on-Ground and Moisture. So everyone assumed by headline reading that moisture underneath the slab was a problem, and they needed to put a vapor barrier underneath to stop intrusion of the moisture, because the moisture would eventually work its way through the concrete, get to the surface, and cause a flooring issue. I reviewed that a couple of years ago, and I was appalled because I never actually sat down and read it. That is not what the study says at all. It says that the moisture coming off the surface of the concrete is what causes the problem, which agrees with all the other studies I've seen recently. It was a misconstrued concept that moisture comes from underneath through to the surface. Now, I've had people say, well, of course it does. I said, no, it doesn't. That is a fallacy. It's a false precept that's just persisted, and we need to undo this. Because if you really think about it, I like what Dr. Joe said over at Building Sciences Symposium just last month, where he said that, moisture in a liquid in a vapor form moves from warm to cool. That's the mechanism. So I asked him, what about the mechanism if it's warm on the surface? He said, well, it doesn't transport them. I said, okay. So he said, the room is typically warmer, and averages warmer than the concrete surface. The concrete surface typically is warmer than the concrete underside. So the movement of moisture is down. It's not up. It's down. So what they're doing is they're confusing diffusion with moisture migration, which I'm not going to get into just right now, because I want to get back to the vapor barrier. So the vapor barrier, as far as I'm concerned, keeps contaminants from the soil getting into the concrete, because there's a lot of stuff in the soil you don't want to get into your concrete, and by diffusion, it will transmit through the concrete. So we have to be careful with that. Right. So I do like it for that point, but as a method of keeping moisture out of the concrete, I could care less. That's not what it's really functioning. That's not what its actual function is. Its actual function is to keep garbage in the soil from getting into the concrete.
Gotcha. Yeah, because that's I was, like I shared with you before we hit record, I was brushing back up on my ACI 302 guide to concrete floor and slab construction, and they as long as I'm reading the most up to date one, but their recommendation is the vapor barrier directly underneath the concrete, and again they're saying that it keeps they're saying the moisture is coming up from underneath, I guess, is what their belief is, their study research is, and what you're saying is you're saying it's coming from above and through the concrete. So yeah, let's discuss this more, because this is I guess when we were looking at that picture that we saw on LinkedIn from Josh, I guess that was like that standard practice on the West Coast, because it seemed to be very popular. I was watching a video of a guy in California, another consultant, and I guess there was a practice of putting a sand layer above the vapor barrier as well, and they were saying that helps draw the moisture out of the concrete, so the concrete cures quicker versus if you put it directly on the vapor barrier.
Yeah, and again, that's another false precept, because drying concrete doesn't make it cure quicker; it just makes it harden quicker. To cure concrete, you want to keep it wet.
Mm-hmm.
Now, if you want it to be a capillary break, which was the original reason for putting that in there, you need a larger stone, because the tighter your pore space, the more capillarity you get. That's just how it functions. That's why you can get capillary movement. You get what's called rising damp. And if you look at rising damp and some of the historical buildings where they're dealing with that, it's almost always on the cool side. rarely ever see problematic rising damp on the warm side of a building? Well, that's because water moves from warm to cool. Well, if the top surface of the concrete is warmer than the underside, what is the mechanism of movement? I can't get any of them to give me a straight answer. They dance around. The reason why you can't give me a straight answer is because that violates the laws of thermodynamics.
Mm-hmm.
What you're confusing is diffusion. How diffusion works with concrete and everything else, and this is what we learned in high school, where if you have two containers and it's connected with a valve, you've got the valve closed. The one side has dye in it, the other side doesn't. You open the valve, and what happens, the dye moves and eventually evens out. That's called diffusion. Well, the water didn't go anywhere. It doesn't have to. It's like a freeway. It allows things to move. That's what's moving everything. It's the water. The water itself doesn't move. And they even and what found the most profound one to me, before I get into some of the more modern ones, there was a 1974 study done by the Army Corps of Engineers. It was for concrete they're going to use in nuclear facilities. So they were exposing the concrete to 150 degrees and above. I think upwards to 160. And what happened, as it kept trying to dry out, all of a sudden it would hit this front, and the water in the center of the concrete would not move or maintain a constant moisture content throughout the duration of the test. They were a little confused by that. If they understood the chemistry of what's going on in there, there's nothing confusing about that. One, water doesn't want to move to the hot side. It wants to move to the cool side. And then what happens with the alkalinity, as alkalinity begins to concentrate as you dry it out, alkalinity has a reciprocal reduction of humidity. So when the humidity is reduced, it means it resists evaporation. And if you keep concentrating it, you can get to a certain point where if you concentrate the alkalinity enough, and this one is a shocker to most people, and the researchers, most of them don't know this, but the sodium hydroxide, the main alkaline component in concrete, it can actually raise the freezing point of water up above 100 degrees Fahrenheit. So the water doesn't behave like liquid water anymore. It's starting to behave like it's freezing.
Huh.
And I tell people, so if you want to, and I really suggest it, is go look at what they do with sodium hydroxide for bulk storage and shipping. They have to keep the lines and the containers heated, because if they don't, at the 40% concentration they have, the freeze point of that water is at 59 degrees Fahrenheit. But sodium hydroxide is weird, because at a lower concentration, at 20%, it will drop the freeze point of water to 13 below zero. And I go, in fact, if you look at the graph, it looks like a drunken mosquito. But as it concentrates past 40%, there's a downward trend at one point, but then it goes back up. You can actually, if you concentrate it to about 80%, the freeze point of water can approach that, what would normally be boiling point. So we're not dealing with water in the same form that we've assumed. And everybody has ignored that, and they're wondering why the concrete won't dry out. Well, it won't dry out because it doesn't want to. You've hit an impasse. Because the other thing is the sodium hydroxide will begin to grab moisture from air at humidities at less than 10%. Even down to 8% relative humidity, sodium hydroxide will pull moisture from the air. So even if you're using desiccators, the desiccant isn't as effective as the sodium hydroxide is. The desiccant inside the concrete is more effective than the desiccant you're trying to use to pull the moisture out. So it's these informational gaps that are leading us to all these speculative, well, how about if we try this? Well, let's do relative humidity as a test. Well, that's one of the dumbest tests I've ever seen. You can't measure moisture or concrete with a relative humidity probe. It doesn't do it. What a humidity probe does is it measures what's supposed to be the balance of water vapor in the pores of the concrete, and that's supposed to be in equilibrium with the liquid water in the concrete, and that's fine in a lab condition because the temperature is the same all the way around the concrete, the relative humidity is the same. It is not that way in a field. It bounces all over the place. And when it bounces all over the place, the response to heating and cooling and wetting and drying begins to change. And they've actually, in the last 20 years, they started researching this, and they've referred to this as concrete hysteresis, where water will be absorbed, but it doesn't, what they call it, ingress, and doesn't egress at the same rate. So they're wondering why it's not doing that. Well, if they look at the chemistry, it makes perfect sense. But they're not looking at the chemistry. Yeah, the alkalinity in concrete has always been an issue, and it's not been recognized and fully appreciated. In fact, in studies, I gave a seminar a little over 20 years ago at the Florida State University, and the engineering department was there, and there's some people from the Department of Transportation. And I told them that basically most of the studies done on concrete in the last 70 years are done incorrectly. And they stopped me and they said, well, how can you make such a broad statement like that? I said, well, if you look at all the studies, every one I've read, they just talk about the hydroxyl ion. And they put it up in this big, nice, neat pile, and then they kind of push it off to the side. I said, the problem is the primary alkalinity, the primary alkaline material that's spun off as cement develops is calcium hydroxide, or they call it Portlandite. Well, that doesn't react the same way to temperature that sodium hydroxide does. Sodium hydroxide gets more active as it gets warmer, and calcium hydroxide goes the other way and it gets more active as it gets colder. And it's actually most active when it's just right above freezing. Well, most of the researchers don't even know that. Why they don't know that is really disturbing to me. They're supposed to be telling us what to do with our concrete. They don't even know what the hell they're testing. I'm sorry, but they don't. I mean, it drives me crazy. But now we'll fast forward to go to 1997. This report came out by VTT talking about where they started using more sophisticated methods of testing the relative humidity as well as using thermocouples. One of the things that they confirmed, and it's been established by the Portland Cement Association and all these researchers prior to that, Powers, and there's all these other names I can't think of off the top of my head, but it shows that when concrete is cured in warmer temperatures, it ends up having durability issues down the line. The warmer the concrete is placed at the time of cure, the weaker it becomes and the less durable it is. And that's been consistent for decades. What they found was, and was shocking to me, and I didn't know this, and I don't think anybody else did, but when they put those thermocouples in there and they put the humidity devices in there, they had one that was embedded and they had some from the surface so they could look at it from two different views. Shockingly, the relative humidity at the surface of the concrete dropped to between 50 and 60%. The reason why that's so bad is cement will not form if the relative humidity drops below 80%.
Oh.
So for the first 2 to 3 weeks, you're not getting any cement development in the top inch of the concrete, or very little. Now, as the temperature increases, that gets worse, and it's a longer duration. And you have what's called a cascading effect, where one influences the other, because as the concrete gets more alkaline, as it dries out like that, the alkalinity by the sodium hydroxide now imparts a hydrophobic response, or basically makes calcium hydroxide insoluble. So even if you put water on it when you're carrying it for 7 days or so, it doesn't make much difference. It will still not develop all the cement it needs to develop. And then in 2006, Dr. Zollinger from the Texas Transportation Institute ran this test because he noticed that there was a gradient portion of the concrete. The top inch of the concrete was having issues. So he did one where he didn't water cure and did water cure for 7 days under laboratory conditions. And the 7-day water cure, when he sliced the top inch off, it was a full 20% weaker in compressive value than the remainder of the concrete. And then over in Portugal, over in the Middle East, over in Asia, they're finding the same thing over and over and over again. So now with the more alkaline cement that we're getting by adding this cement kiln dust, we now need to move towards internal curing of concrete. Surface curing will not get it done, period. You can cure it blue in the face. It won't get it done.
And where's the alkaline coming from?
The alkaline is coming from the cement. Now, the thing is, the ready-mix producers are being victimized by this because they're supposed to divulge whatever admixtures or anything else that's extra in the concrete. But since this is added at the time of the cement production, they have no knowledge of this. They don't know what's in it or how much there is in it. So they're probably seeing problems, and they're just going, maybe we're doing something wrong, and they don't want to talk about it. Well, these are things beyond their control, and if they're made aware of this information, they can make corrections because you can internally cure concrete. Now, one of the things that really cracks me up is expanded clay, shale, and whatever else it is, where they make all these lightweight aggregates, and they were shamed back in the day saying, well, you can't use those aggregates because they contain water and it makes the moisture problems worse. Actually, they're finding now that when you put this absorptive aggregate in the concrete, it helps internally cure it. And you end up getting a better piece of concrete. So they inadvertently headed in the right direction, but it's not distributed well enough. So there needs to be other factors involved where you start adding materials to the concrete that don't interfere with water-cement ratio, but act as a water reservoir to help cure the concrete. The technology is there. It's just not.
Yeah. But what are they doing during this cement manufacturing process to get the alkaline in it? What's changed over the last 20 years that it's causing that?
That's kiln dust. That's been required by the EPA. The EPA said you got to recycle this stuff. A lot of it goes into waste, and they're trying to figure out other uses for it. But a certain percentage of it gets reintroduced back into the cement process. So all the cement we have now is more alkaline. Now, what's really funny is the concrete and cement industries came out with a kind of a tepid announcement that no more low alkali cement will be offered. Well, the reason why it's not offered is because you can't make it anymore. It's because of CKD. The cement kiln dust doesn't allow for low alkali cement. You can't make it anymore. It doesn't exist.
So the EPA is requiring them to use the CKD?
Yes, that's the requirement. And so that was taken out of it. They fought it. The first big fight was back in 1990, so they were able to delay it for another 12 years. Because the one concrete company said, look, our entire business is based on low alkali cement. We have to start making changes before this is enacted. So they gave them time to make the changes they needed to make.
Do you know what the purpose of the EPA? Yeah. What was the purpose of the EPA requiring that?
It's because of the flue gases, because this came out in the flue gases and was polluting the air, and was the carbon footprint and all that stuff. It's all environmentally safer by recapturing the flue gases. And part of the flue gases is cement kiln dust.
Oh, okay. So they're capturing it and it's falling back into the processing. Is that?
They're actually adding it back in.
Oh, they're actually adding it back in.
They're actually specifically, purposefully adding it back in.
Okay. So they're capturing it and reusing it, and that satisfies what the EPA requires.
Yeah, and it doesn't affect the 28-day required compressive value of 3,000, 4,000, whatever they're aiming for, but it does hurt the concrete for its long-term durability. That's why we're seeing concrete now, even if you're placed it exactly the same way you did 20 years ago, it's not as durable. You're seeing problems with it early on where you get washout and everything else, and you're getting early ASR. A lot of surface ASR is occurring. They call it near surface alkali aggregate reaction. And that's all because of the higher alkalinity. This higher alkalinity is what triggers the damage.
Yeah. Remind our listeners what ASR is.
It's alkali silica reaction. And basically, that's when the alkalinity in the concrete starts dissolving some of the softer aggregate, and usually the smaller and amorphous aggregate goes first, and that's all the stuff that floats to the top. So as you see, when you get decracking, ASR, and all this other stuff on your concrete pavements, it's triggered by this. And now the trigger is much higher. So this triggers harder, faster, and earlier than it used to. So we have to compensate for it, or we're going to just be in a world of hurt. Because they're already placing concrete that needs to be repaired in as little as 12 years on roads and bridges. That's ridiculous. That was not like that in the past.
Yeah.
But if we internally cure it, that will keep the alkaline from concentrating. It doesn't move. Because when you internally cure concrete, what you do is you've eliminated a lot of the freeways that we normally have. You're reducing the capillaries in both size and connectivity. And it keeps the alkaline from increasing because they're all scattered. They can't gather and concentrate.
Gotcha. So I didn't catch that last part. How do you separate them again?
By internally curing the concrete. That is really the only way we're going to be able to fix this. So that's my biggest emphasis.
And the internal curing, and that's introducing what into the concrete to have it internally cured. What is
my two favorite materials? But they have to be engineered correctly, because if you do it wrong, you can cause uneven stresses in the concrete. So that needs additional research, and they have to verify what they're doing. Don't use something that hasn't been verified, because there's a lot of, let's say, just overly enthusiastic people selling something they don't quite understand. But yeah. I like the combination of absorptive aggregate, because you can actually have normal weight aggregate but still absorptive. And I think it's a great, great idea, along with what's called a colloidal silica. Mm-hmm. Now, the colloidal silica has to be engineered properly to where it doesn't react too quickly, or it tends to not behave in the manner that you really want to. I don't want to go into that, because people would borrow off that and they'd use that to help sell their products. So I'd rather not share that.
Right. Yeah, we've had some colloidal silica internal cure folks on the on previous podcasts. So when you say aggregate that absorbs, what kind of aggregate is that? The clays you mentioned before, or?
Yeah, and also there's other types that that are limestone based. There's other ones that are semi-permeable, and those all really help. They don't hurt the water cement ratio, because the water is essentially, because if you soak the aggregate and you let it air dry and then you add it to the concrete, you're not adding to the water cement ratio. But what you're doing is you're adding reserve, because what happens as the cement formation occurs, it absorbs water from the mix. Well, unless you have something to replace it, the concrete begins to dry out. So if you have an aggregate where there's a moisture reserve, it will pull to that area and keeps replacing the moisture to get a more complete reaction of the cement. And it helps cool it. Now, internal cooling, that's called the evaporative cooling effect, which has not been studied by these researchers and really irritates me. That is one of the most effective ways of getting concrete to really get dense all the way through, where we get a more uniform, more homogeneous mix. And the smaller the particles, the more surface area you have, so the more evaporative cooling effect you get.
So the aggregate acts as like you were saying, a reservoir, and then it when the cement needs it, it pulls it from there.
Yes.
Yeah.
It's got a reserve. So instead of it drying out, because unfortunately the pozzolans they put in, their dryad pozzolans, they actually start competing. So what will happen is they actually make the concrete worse if you don't get complete hydration, because they're dependent upon the initial cement formation to produce anything beneficial. So the pozzolans are actually making the concrete worse, when in the past they made them better. So it's we're really kind of upside down on all this. We need to reboot.
Yeah, it sounds like it.
And here's the moisture testing. That's why it's so convoluted as well. Well, it's the top 1 inch surface of the concrete where all the problems are occurring. Well, when they do a RH probe test, they drill in 2 inches, they completely bypass the problem there. So, oh, look, it's great. It's not great.
one little test and how many square feet?
Well, yeah, and that kind of doesn't matter. So that's why I like a concrete meter, because it'll measure the surface moisture. It measures in about 3/4 of an inch, because that's really where the problem is. Mm. And I don't want to be proprietary, but one company did do that, and it was tested in Finland, where they weighed it against gravimetric. Gravimetric is the most accurate way to test moisture in practically anything, because they put it in an oven, they dry it out, and all the free water is removed. And that one product, it was brought out in the field because there were some other products that agreed fairly well with the gravimetric in a laboratory setting. But boy, when you took it in the field, the results started going all over the place, and only the one product kept in alignment with gravimetric. So that's what I'm telling people. I said, do not base anything on a laboratory study. You bring it out in the field first. Then what you do is you bring in the laboratory to evaluate what you're looking at, and then you can look at the mechanisms. Everything I've ever seen that's first developed in a laboratory, they end up screwing up, and it's the customer is the guinea pig. The person who develops it should be the guinea pig, not the other way around, where it's the tail wagging the dog right now.
Yeah.
And if we bring this back to fundamentals, the flooring industry over the past year, by some of the flooring manufacturers, said that the claims have now hit $3 billion a year. 20 years ago, it was $1 billion a year. Well, it's accelerating. It's good. I expect it to triple again unless they do something dramatic and change what they're doing.
Yeah, you would think the insurance companies would be jumping in and pushing this.
They should, but it's a matter of getting to that's a great idea. Because if the insurance company knows there's a way to fix this, they could put some pressure on it. But I am working now with IICRC and working with some other groups where they are recognizing the need to start changing things. Because when these international studies all agree with each other and they don't even know of each other, that's pretty compelling when they keep getting very similar results.
Yeah.
And there's a consistency problem. And all the moisture problems, again, follow the laws of thermodynamics. It goes from warm to cool. But it's soaking into the surface. And one of the ones I love to use, and please feel free to use this as well, as a demonstration to your clients and anybody else you talk to. There have been some NBA games and even college and high school games all through the country that have had to be canceled because what will happen, it's like this one thing, it was the Timberwolves versus the Knicks or something like that, or the 76ers. Well, they forgot to turn on the HVAC system. So people were coming in and the air was too warm. And with all the people breathing, the cold surface started getting wet. So they kept mopping it, putting fans on it. They take the fans off and get wet again. They keep doing it. So they finally had to cancel the game. That moisture was coming from the air, 100%.
Yeah.
So if that was a bare concrete surface and you were working on a job site, you would have never even seen that. All that water would have soaked into the concrete. And if you'd run tests prior to that, and then subjected to all those environmental changes, by the time you put it in the floor, it'll fail. That's where almost 100% of the failures are coming from.
Huh.
Completely avoidable.
Yeah. So let's circle back around to the vapor barrier where we started this conversation. So what should we be doing? I mean, differently than what we're doing right now and what ACI 302 is telling us?
Yeah, I would put a graded, large to medium aggregate underneath the. I would put the vapor barrier down and put the large aggregate over there. Graded aggregate. Make sure it's self-compacting. I don't like sand because it won't compact. It's got to be a graded aggregate. That acts as a capillary brake. It gives the water somewhere to go. Because the water from underneath is not going to magically make its way to the surface. that is a false precept. I've never seen any compelling information that has convinced me that they can go against the laws of thermodynamics and the moisture magically goes through. They're confusing moisture migration with diffusion.
Because we're saying the warm,
yeah,
because the warm air is going to where it's cooler, and that's where the water is concentrating. That's what we're seeing. Physically, visually seeing is the water beating up on the concrete, and we're thinking it's coming from within. But what you're saying is it's the warm air coming down to the concrete. That's because that's where the cooler temperature is.
Yeah, correct. And that's why propane heaters are such a bad idea. Because propane, if you're trying to warm up a room, it's a really good way to feed the concrete a lot of water. Because the main exhaust of propane is water, H2O. So it's about a 9 to for every 10 units of consumption of propane, 9 units are converted to moisture. So you don't want to do that. Now, I was in this high-tech facility. I'll give a couple examples. Well, we went in there, and the floor had failed. And the inspector they'd hired said it needs to be moist. They need to put in moisture mitigation because the moisture is too high. Well, I looked at the concrete mix design back then. I said, there's no way it can be that high. I said, that's got to be a ambient moisture condition or something came in from the top. And he said, no, everybody knows the moisture comes up from underneath. I said, not with a 0.45 water cement ratio. No, it's not going to happen. I said, and then what I did is I brought in a device with me. I had a digital hygrometer and an infrared thermometer. And I took a shot of the temperature of the concrete as well as the air. I looked at the digital hygrometer. While we were talking, we were in this small room, and there's a bunch of us in the room. I said, okay, the 15 to 20 minutes we've been in here, the relative humidity in the room climbed from 52% to 78%. We're now in an active moisture condition that the concrete's going to be drawing moisture into it because we're within 10 degrees of dew point. If you're within 10 degrees of dew point, you can almost guarantee you're going to have an issue. So I said, I know what happened then. So let's duplicate what they did, but this time we're going to monitor the room. So we monitored the room. We had them spread the adhesive. The relative humidity in the room climbed over 90%. I mean, it's like a sauna in there, even though it was fairly cool. And of course, the floor failed just like I predicted it would. So because you're adding water back into the concrete. So we dried out the concrete because it was a water-based adhesive. I stuck the digital hygrometer underneath the lid, and it jumped up almost to 100% right away. I said, because there's water in this adhesive. I said, yeah, it's 10% water. I said, there we go. There's our water source. So what we had them do is dry the concrete back out. We measured the concrete, made sure it was under 5% under 5% moisture. Then we brought in dehumidifiers as well as air movers. Put the air movers across the concrete. That's what helped dry it out, because that's the other thing. When you're trying to dry out concrete, you need to move air, especially across the surface. The coolest portion of the evaporation process is right at point of evaporation. That's why sweating cools us off. Now, if you separate it, you put it out here, you won't cool off. So what you want to do is you want to remove it. So by blowing air across it, you remove the evaporative cooling effect and makes the evaporation more efficient. So you remove more water much quicker. So we brought in the dehumidifier. We kept the dehumidifier between 55 and 60%. They installed the exact same floor. It was so well bonded, they couldn't pull it off the floor. They couldn't get it off the concrete.
Yeah.
And they didn't need any moisture mitigation, but the default is to moisture mitigate because, it must be coming from the concrete. No, almost all of it is coming from the air.
Is that air? That's air that's blowing through the HVAC. It was in that case, or just ambient.
This moisture was actually coming from the adhesive itself. The adhesive was providing its own moisture problem. Warm surface gets sucked in. Yeah. So,
we talked about the adhesive water problem on another podcast. That's why I chuckled.
And why does it do that? Because the concrete's colder. If the concrete's warmer, it wouldn't soak up the water from the adhesive.
So what? I guess just something jumped in my head. So the concrete being cooler is the problem. What are your thoughts on the heated floors, like running the heated tubes through the floor, and using that as your main source for heating a room versus blowing, the American way, which is blowing hot air through the house or through the building and everything like that. Using that, and then I guess having, you were saying, what's good is also circulating the air. So having ceiling fans or something of that nature, moving air through there. Is that a better approach to kind of help solve this problem? Or
yeah, I think so. Because if you could get the concrete and the air temperature where the relative humidity in the air is below 60%, and you've got the temperature of the concrete close to that of the air, you're not going to have an issue. Because one of the things I keep hearing is these moisture-sensitive adhesives. Well, that's a bunch of hogwash. What I've done is I've taken these moisture-sensitive adhesives, I've laid them up on cement board, and as long as they cure and set properly, they're very water resistant. I stuck the same ones into a bucket and left them for a year. Not a darn thing happened.
Yeah.
Not a thing. So what happens if you put it down, though, and there's moisture in there, that moisture is going to prevent a good bond, and it's going to prevent it from actually setting and curing properly in the first place. That's what causes your blisters and epoxies, because you have too much moisture in there.
Yeah. Huh. So the vapor barrier, obviously, or what we're saying today is we're putting it down for a reason that might not necessarily be helping with that reason. So here's a crazy question. What's the point of putting the vapor barrier down? Is it just to block like radon or whatever coming out of the ground, or?
Yeah, well, if you got radon or you got contaminants, but if you put a good capillary break, you don't have to worry about the contaminants because there's no pathway for the moisture to move through.
So what would that be instead of a vapor barrier? What would be a capillary break?
Good crushed rock, like DT.
Oh, that's what. I'm not trying to put Stego out of business. I'm just asking questions.
Stego is great for keeping. If you're in an area that used to be farmland or they used to grow crops, absolutely use a vapor barrier. And if you're in an area where you're close to where there's a dump site or there were a lot of plants and you don't know what's in the soil, I would use a vapor barrier, not for keeping the moisture out, but for keeping garbage that's in the soil that shouldn't ever be in concrete, because that will transmit very quickly, because that's where your diffusion comes in. When there's something that's water soluble and enters into concrete and it's now invasive, it goes from higher to lower. So what it does is starts working its way through. That can work its way to the surface of the concrete. I have seen that.
Yeah.
In fact, I saw some efflorescence at this place over in El Centro, in just outside of San Diego, and they couldn't keep the epoxy floor down. So look at all the alkaline efflorescence. I said, don't always assume it's alkaline. I says, especially since this used to be crop. They used to grow crops, orange trees, and everything else out here. So sure enough, I did a pH test on the so-called alkaline efflorescence at a pH of 3. So it was actually destroying the concrete itself. The concrete's pocked and marked and weakened, and that stuff worked its way through the concrete. It was 30-year-old concrete, but is now starting to break down because it's so contaminated.
Huh. All right. So we're saying use the vapor barrier, but maybe not the way we've been using it before, and not put it.
Put the capillary brick back down on top of it and put it where it's supposed to.
Yeah.
It should be.
And then that will putting the vapor barrier below the crushed stone layer or granular layer. would help with the other issues that we're seeing in concrete with.
Yeah, and if you look from the year 2000 earlier, ACI required a capillary break on top of the vapor barrier. They required it. That you would get in trouble if you didn't do it that way. And all of a sudden it reversed. And they reversed on a false precept.
What year was that?
Prior to 2000, year 2000 earlier, I think it may have been even as late as 2002, but prior to that, they required a capillary break over the vapor barrier.
Huh.
It gets really interesting, doesn't it? When you start looking at history.
It does. I was enjoying the. It's been a while since I looked at ACI 302, but I did like their chart where they kind of explain when to use a vapor barrier, when not to use, how to use it. But it seems like there's language in here that says, basically it's saying that this is very controversial, is what it says in ACI 302. There's still discussions being made.
Well, the reason why is because it violates the laws of thermodynamics, how the moisture supposedly magically makes its way from cool to warm.
Yeah. So if you were consulting on like what's been popular lately with the warehouses and the distribution centers, you would have them put the vapor barrier below the base, and
Correct.
then okay,
correct.
Huh.
Because they said, well, what about the water that can get in the crushed rock? So concrete loves to stay wet. You keep it wet. It's like if you look at some of these tunnels were built back in the 50s and 60s, that concrete that was originally 2,500 PSI, it's up around 8,000 PSI now because it's maintained a wet condition. Concrete wants to be wet. Let it stay wet. Just don't allow the water to move.
Yeah.
The simplicity of this is to let's get it in the condition it wants to be in, and let's get it in a condition where it'll tolerate something that doesn't like water.
Yeah. No, I think that's this was a great discussion today, Robert, but I think this is a good spot to pause for today. We'll have to pick it up again. So are you participating in anything that is doing studies on this, or
Yes.
you are? Okay.
Yes,
and is it ACI driven, or is it from someone on? No.
They're not real happy with some of the stuff.
Yeah. Okay. So if folks that are listening to this, they want to reach out to you and learn more or support you and what you're doing, what's the best way to get a hold of you?
Probably my email is rcconsulting.higgins, HIGGINS, @gmail.com.
Okay. Yeah, I'll put that in the show notes so when we put this out, people can get a hold of you. And he's also Robert's active on LinkedIn, like I said. So give him a shout on there, reach out to him, connect with him. And this was as nerdy as it sounds. This was this was great stuff. I didn't think we could talk almost an hour on vapor barrier.
You're talking to a fellow geek. I mean, I geek out on it constantly.
All right, Robert. Thank you. And we'll have to do this again.
Okay, sounds great.
Thank you for joining us for another Concrete Logic podcast episode. If you got some value out of this or you enjoyed it, please share it with others. And if you could take a moment and give us a 5-star review on your favorite podcast listening app, I would appreciate it. We will catch you on the next episode. And now Mike Dunton's going to take us out. That alarm always sings couple hours before the sun comes up. Open up the side, put some diesel in the lights and wait till the trucks roll up. Yeah, this ain't how most folks live their lives, dripping in sweat, working overtime. But while they're tying their ties for their 9-to-5s, we're out here changing these skylines with wood, iron, and mud. We work hard for $1, give thanks to the
It's written in our blood with wood, iron, and mud. From the swamps to the city, from the Lone Star heat to the woods of the Georgia pine. Good old boys and girls who ain't afraid of getting dirty for a clean time. And if you want to see the fire in a grown man's eyes beneath the hot summer sun, find the wild-eyed boys clocking days and nights, working hard to get that job done with wood.